So, Wednesday we were talking about this idea that, you have a parabola you want to graph, and you want to find out where the vertex is. That's the first thing. And you'd like to put it, the equation to the form y minus k equals kx minus h squared, so that we know that h and k are the coordinates of the vertex. And then there are other things we can do, such as look for the groups. And we also know, based on the A, whether this is going up, and also a little bit about its shape. If A is greater than 1, then it's going to go up a little more steeply. If A is less than 1, it's going to be gradual. If A is negative, it's upside down. So we're just going to, beat this almost dead horse with a stick here just a little bit more. We're going to look at this step a little more abstractly. Again, I have this equation y equals ax squared plus dx plus c. This is the rule of my function. I'm graphing it, so I'm using y here. And I'm going to start trying to get it to look like this by subtracting c from both sides. So I have ax squared plus dx. And then I want to see if I can't, put this into this form, for which I'm going to have to complete the square. So first I want to factor out the A. And then I want to think about, what do I have to add to this expression here to complete the square? Well, we take the coefficient of x, we divide it by 2, and we square it. So b over 2a squared, that's the magic number to complete our square. Well, I have to add it to both sides. But wait, careful. B over 2a squared times a, right? So this is times, I didn't add b over 2a squared, I added this times a. So that gives me a times b over 2a squared on this side. All right, now I can factor this, because it's a perfect square. This just becomes a plus x plus b over 2a. And now I want to manipulate this a little here. This is b over 2a squared is b squared over 4a squared, but I'm multiplying by an a, so that only gives an a. So I'm going to get b squared over 4a. It's a plus, and then minus c. Okay, I'm almost where I want to be. Actually, I want to subtract here, so c minus b squared over 4a. And I'd like to have this over a common denominator, so this is going to become 4ac over 4a minus b squared. Okay, this is exactly what I wanted. me write this as minus a negative, right? So now I can see my h is minus b over 2a, and my k is this ugly guy. So wherever this parabola happens to be graphed, I know that my vertex is at negative b over 2a, and the value of that vertex, the maximum or minimum of the parabola, is going to be 4ac minus b squared over 4a. Okay, so I have an equation, and I know where the vertex is. Now, let's be a little practical about this. While this is kind of reminiscent of something that's part of the quadratic formula, it would be pretty hard to remember this. You could memorize it, but the x value is not that hard, minus b over 2a. So, given some random quadratic function, I at least can find the x value, right? The place where the axis of symmetry would be. And I can always just plug this back into my equation to find this value here. If I were to plug minus b over 2a into this equation, you would certainly expect to see this. So let's try an example. My function here I'm going to graph is 5x squared minus 30x plus 49. So first thing I want to know is the x value of the vertex. And I know that's negative b 2a, so that's going to be 30 over 2a is 10 is 3. Okay, so let me just write this. Vertex is at 3 comma, well, 3 comma what? I plug it in, up with 3, it's going to be 5 times 9 minus 30 times 3 plus 49, so 45 minus 90 plus 49. 45 plus 49, that's 94, minus 90 is just 4. Okay, what else do I know? I know my a is positive, it's going to go up. And since I have a value greater than 1, I know it's going to go a little faster than usual. I might be able to find the roots. I can check that, right? I can check real easily to see if it's going to have real roots. I can look at the determinant, which is b squared minus 4ac. That's the part of your quadratic formula that's under the radical. So that's going to be 900 minus 4 times 5 is times 49. So 20 times almost 50, that's like 1,000. It's almost 1,000. So this is going to be negative. Determinant is negative, so we have no real roots. So that's not going to happen. All right. I'll go over here. So now I have almost all the information I'm going to get. I can, plug in. Wish I would have done that. I have the vertex. I can plug in a value on either side, right? So a good value might be where the vertex is +1 and -1. So that would be f of 2 and f of 4. That'll give me a feeling for the shape of this. So 2 would be 5 times 4, which is 20, minus... You do that wrong? Minus 60 plus 49. That's 69 minus 60 is just 9. And I could plug in, you don't have to plug in 4, do I? Why don't I have to plug in 4? It's the same on the other side, right. I picked this number here. Well, I know it's symmetric. Well, but maybe I made a mistake. Maybe I want to check my work anyway. Okay, 16 times 5 is 80 minus 150 plus 49. So that is 199 minus 80. No, I did something wrong here. 80 plus 49 is 129. What did I do wrong? We'll look at that in a minute. I guess this would be a waste of time. Unless I did something wrong with this. 4, 5 is 20, 60, 69. Well, it's early in the morning for me. I like to sleep until 2 in the morning, but I can't anymore. All right. Let's put a graph out here. So my vertex, I believe, is at, what did I say? It's at 3. 4. 1 point. I think my point 1 to the side of 2 should be 9. So 4, 5, 6, 7, 8, 9. And I think that this point here should be the same. This is bothering me. 16 times 5 is definitely 80.
You put 150 was 120. 30.
Minus 120, thank you. 5, so 80 plus 49 is 120. Okay. These things should bother you too, right? That's how you kind of focus in on getting the right answer. I mean, if something feels right, okay. If it feels funny, find out what the problem is. Okay, so there's my parabola. Just as I said, there's no roots. It doesn't go through the x-axis. So, all right. Negative b over 2a, worth remembering. That's where the x coordinate of the vertex is. All right. Any questions on quadratics? Because we're going to move on. Okay. We're going to now talk about a more general polynomial. So today we're going to start looking at how to graph a more general polynomial. We're going to look at some features. We saw on Wednesday how to graph a second degree quadratic function, And today we're going to look at something a little more complicated. I'll just put up an example that we're going to get back to in a bit. So, okay. So this is a 5th degree polynomial. And this is an example, but really any n greater than 2. Right? It could be 5, 102. What we're talking about now is going to apply. We're going to put together a toolkit of things that will help understand the graph, help us actually graph it. First item is called end behavior. So by end behavior, what I mean is what happens to this function out in the positive x direction or in the negative direction. Now, the key point to realize is that here we have what they call the leading term, x to the 5th, that's 5 being the degree of the polynomial. This term, as we get out on the axis, on the x-axis in either direction, is going to dominate. I want you to think a little bit about that, why that is. Let's say I had a polynomial, let's say x cubed plus 1,000,000 x squared. Well, for a long period of time, this term is going to dominate because the coefficient is very large. But eventually, as I get far enough out, that will no longer be the case. And you can tell right away, in this case, where that will be. Right? Out at about 1,000,000. Right? At 1,000,000, this will be 1,000,000 times 1,000,000 squared. But this will be 1,000,000 cubed. At that point, they'll, x cubed will have caught up. And thereafter, if we get to 2,000,000, well, this is just 2,000,000 squared times 1,000,000, but this will be 2,000,000 cubed. So the leading term will dominate at some point. And when I talk about end behavior, that's what I'm talking about. What happens out here when that term starts dominating? So this is actually pretty easy to see what's going to happen. There are two cases. One case is the leading term has an even coefficient, exponent, sorry, or it will have an odd exponent. In addition, we have to look at the coefficient, whether the coefficient is positive or negative. So let's create a little table here. So let's say the coefficient is positive. And let's look at what happens when this is even. Even number like 2 or 4 or 6. So as x gets very large, what happens to the function? So in my example, I have, say, positive coefficient and an even exponent, and I put a very large number in here, what happens to this term? It gets very large, right? F of x is going to go to infinity. As x goes to negative infinity, that is, I put a very large negative number in here, what happens? Well, it's even, right? So the negatives cancel. And it again gets very positive. So again, the function will go to infinity. Okay. That's for a even exponent. Now, if the coefficient is less than 0, then just the opposite is going to happen, right? As x gets very large, f of x is going to get very negative. That would be kind of going down like this. And as x gets very negative, f of x is still going to go very negative, right? When this is even, the sign of x doesn't really matter. Okay, that's the even case. How about when x is odd, like in this case? Okay. So again, if the coefficient is positive, this is odd. As we go out in the x direction, what happens? What happens to the value of the polynomial? I heard that. It's very large. Oh, this.
I think it's small.
As x gets very large, 3x to the 5th is going to get very large, right? So in this case, as x gets very large, f of x becomes very large. But now, if we go off in the negative direction, what happens here? The negative signs don't cancel. It still gets very large, but it gets very negatively large. So in this case, as x goes to a negative infinity, f of x also goes to negative infinity. And then finally, the fourth case is, well, what if this coefficient is negative? Well, then it's just the opposite. If it was positive, x getting very large, f of x will go to negative infinity, will get very negatively large. X goes to negative infinity, it'll get very large again. All right, that's a very general way of stating it. What's a good way to remember? Think of things that you know really well. Let's take f of x equals x squared. Here, the exponent is 2 is even. And we know that as you go off in the x direction, in the positive direction, this gets very large. But if you go in the negative direction, it also gets very large. That's its end behavior. It's kind of a parabola. It's almost nothing but end behavior. If I put a coefficient, a negative coefficient on here, then just the opposite would happen. So f of x equals x squared is a good example to think about when you're trying to remember what happens when the exponent is even. Now another good example to keep in mind is, for odd, is f of x equals x cubed. And now you should know that that kind of looks like this. As we get positive, it goes off and it's positive, but as we get negative, it goes off and it's negative. And if I were to put a negative sign here, if I give it a negative coefficient, well, we would get a reflection, and the end behavior would be just the opposite. Okay, so that's just the end behavior. That doesn't really tell us what happens in between. In between where this leading term becomes dominant. So we're gonna look at that a little too. We're gonna look at that next. Any questions about end behavior? Yeah, it's, if you think about it, nothing real complex about it. It's pretty straightforward. Okay. The next thing I want to talk about in our toolkit is the zeros of the function. Where I talk about what we do with the zeros, I want to clarify. There's a few different terms I use interchangeably that pretty much mean the same thing. If I talk about the zeros of the function, what I mean is values, say, of c, where f of c is 0. It is 0. Sometimes I'll also use the term roots. We're looking at the roots of, the equation f of x equals 0, or, in this case, minus x to the fifth plus 3x cubed minus 2x equals 0. So, roots of the equation. Another term I might use, which a little faulty if I'm not careful, I could say solutions. Well, I mean solutions of these two equations. I should say that. I should say mean the solutions of the polynomial equals, function where the function equals 0. So these are all just kind of names for these points. Another thing I could say, numbering is funny, so they match what the book has to say about it, is x-intercepts. All right, let's see why these are the same things. Same thing. Where this function happens to, hit the x-axis, right, is where if I have some value, say a, or b, or c, where f of a equals 0, f of b equals 0, or f of c equals 0. Okay, those are my zeros. But they're also the place where the graph is either going to just hit the axis or go through the axis. So these are the x-intercepts. I guess actually the way the book likes it, this is 1 and this is 2. I think 1, 2, and 4 are really obvious. Number 3 isn't quite as obvious, right? if I have, some 0 at x equals c, or an intercept at x equals c, I know that x minus c is a factor of f of x. Okay, let's think about that for a second. When we have a quadratic, x squared minus 2x plus 3, right? That's my function. And I want to find a solution where this equals 0. Well, my first step is usually to try to factor it, right? If I have 2 factors, each of them could be 0, and that's where my zeros are. That's where my solutions are. Well, that holds for any degree polynomial. I want to be clear. What I just said is one direction. I said, if I can factor this, that's where the solutions and the zeros are. Now I'm going to say the opposite. I'm going to say, if I have a solution, c, then x minus c is a factor. Now, that's not so obvious, and it really requires a proof. But we're not going to do the proof. Requires a little more algebra than we have at this point, but there is such a proof. I think it's worth noting that when, sometimes we solve this and we can't really factor it easily, so we use the quadratic formula. And sometimes with the quadratic formula, we'll find that we get 2 roots. We might just get 1 root, like in the case of f of x equals x squared. Or we might get no roots, which says that our function doesn't cross the x-axis at all, right? We could have a parabola like this, or like this. There is a neat little mathematical pearl here. And I don't want to get by without pointing out. This can only happen if my leading term has an even exponent. That is to say, if the leading exponent is odd, right, the end behaviors will always be opposite. What does that tell me about this function? It has to pass somewhere, it has to pass through the x-axis. So if you have a polynomial with an odd leading term, you know there's always at least one real root. There may be more, it's always going to be at least one. So that's a nice thing to know. I said that, but I left something out. How do I know that my function doesn't, kind of like a piecewise function? How do I know it just doesn't jump over the x-axis? Any thoughts on that? We don't really know why yet, but does anyone have any intuition? You guys have been dealing with these a long time. Haven't you noticed something about polynomials in their graphs? They never do this, do they? They never jump. Right? Again, this is something that kind of begs for a proof, but we're not at the right level for that. Take pre-calc, take calc, and if you're interested in being a major, you can take a class called analysis and we discuss this. But polynomial functions are all continuous, right? They don't jump off the page. And, you know, they're also smooth, right? You don't ever see something jagged in a polynomial function. So that's something you run into. You will run into this in calculus a bit, but it just so happens that any polynomial function will be smooth, just as it will have an in behavior. Okay. So again, the point is that I was making, the bigger point was, if there are zeros, there are places where this is equal to 0. We now know where the graph is going to cross the x-axis. We'll use that when we try and graph. A second here. Something else came in. Here. Next item in our toolkit has to do with the behavior of a polynomial. It again has to do with zeros. If I have some point on my polynomial here, let's say point A, so the function has value f of A, and that function happens to be greater than 0. I have another point, B, so it has the value f of B, that's less than 0. There's something we can say about what happens between f of A and f of B. Again, because we know this function is a continuous line and it doesn't jump around, we know that somewhere between A and B, we have to cross the x-axis. We have to have a 0. So, you know, if we try and factor this, we find we can't factor it very easily. We can't find the zeros very easily. We can narrow it down if we can find these points f of A and f of B, where the value of the function switches sign. This has a name. This is called the intermediate value theorem. The book calls this the intermediate value theorem. This is actually just part of the intermediate value theorem. The real intermediate value theorem says that you have this condition f of A is greater than f of B, right? That every value between f of A and f of B is crossed as the function goes between them. Maybe crossed more than once, but this is the part of the intermediate value theorem we're interested in, the fact that you can kind of hone in on a 0 by finding points on either side that go positive to negative. The elaborate statement of this kind of looks like this. It says if A is not equal to B, f of A is less than f of B. I'm going to do it the way the book does it. greater than 0, f of b is less than 0, then, I don't know if I've used this symbol that says there exists a c such that f of c equals 0. That's the orthodox way to describe this. Okay, that's the intermediate value theorem. It's another tool we're going to use when we might use when looking at polynomials. This. And there's one more tool which is very related to the intermediate value theorem. It's kind of the other way of looking at it. It says if I have 2 points, I have an A and a B, there are zeros. F of A equals 0 and f of B equals 0. Then it says that on this interval, A to B, actually, to be more accurate, the open interval, A to B, not including A and B, there exists a C such that f of C is a maximum or local maximum or a local minimum. Well, let's think about that. We know the function kind of connects these 2 points somehow. It could be above the axis, it could be below the axis. It could actually go up and down along the axis. But we know that there has to be some local maximum or some local minimum. That's useful because if we have 2 zeros, we know between them we can look for a maximum or a minimum. Again, we're going to do this in this class somewhat approximately. In the next class, calculus, we learn a really new way to zero in on that, unintended, zero in on the maximum or minimum. So, I guess I'll just say a max or a min exists between zeros. All right, that's our toolkit for now for graphing a function. Let's go back to that example I started with. F of x equals minus x to the 5th plus 3x squared minus 2x. Now, to be clear, we could just call out our graphing program and that would show us what this looks like. But we want to know how we can determine this on our own. I mean, if it is we're on a desert island and we need to graph a polynomial function, so that would be high on our list. So the first question now is what is the end behavior of this function? In other words, what happens is x gets very large or x gets very small. Well, you see this is an odd value, right? Yes, Kira?
It's going to get larger in the other direction. Larger in the other direction.
Yes, exactly. the negative direction, right, x to the 5th, you get a negative number, but because we have a negative coefficient, it's going to get very positive. Thank you. What happens is x gets very large in the positive direction. Someone who's sleeping right now, answer the question, please. Please. Chang Ping, do you have any ideas? What's going to happen? As they go off into the positive direction?
Decrease.
Increase?
Decrease.
Decrease, okay. Anybody else have any thoughts on that? Does that sound right? Yeah, this is, again, it's an odd exponent. Okay, we don't really know where this happens yet, but at least we know what it is. Next thing on our toolkit is the zeros. Let's see if we can figure out what the zeros of this function are. Well, is that the function I wanted to Okay, so this is an x I can take out, right? Let's take out negative x. It's a little nicer. X to the 4th minus 3x squared plus 2. Okay. Any thoughts on factoring this? Yeah.
Could we substitute it with like y equals x squared?
Yeah. This is disguised quadratic. You can do that. You can substitute. But I'm going to skip that step. I'm just going to say this is x squared, and let's try 2 and 1. They're both negative. This is positive, but this is what I get. Okay. That's really convenient. I can factor both of those, can't I? Yeah, Midori? You have a question?
Wouldn't it be x squared minus 4x?
I can't hear you over the highway.
Wouldn't it be x squared minus x?
Oh, yeah. I'm sorry. I guess I didn't hear what you said.
I was just wondering, like, because in the middle term is 3x squared, so
Yeah.
wouldn't it be x squared minus x?
Okay. Let's FOIL this, right? To check. Right? First, that's x to the 4th. The outer is negative x squared, negative 2x squared. The inner is negative 1x squared. And the last is plus 2. So that's x to the 4th minus 3x squared plus 2. Is that clear? All right, so these two guys you should be able to factor in your sleep. At least the first one is x plus 1 times x minus 1. And this one's a little harder. This is x squared minus square root of 2 squared, so it still fits my a squared minus b squared pattern. X plus the square root of 2, x minus square root of 2. Oh, so I have 5 zeros, which is the maximum I can have for a 5th degree polynomial. So let's put in those points. 0, I guess I should put a scale on here. 1, Actually, I'm going to make my scale a little bigger because I can see what's happening here. So this is 1, 2, -1, -2. So at 1 and -1, I have a 0. Square root of 2. Square root of 2 is about 1.4. So got another 0 here, and another 0 here, and I've got a 0, 0. Okay. Well, let's think about this for a second. Between 0 and 1, there has to be a maximum or a minimum. So let's just try some value in the middle. Let's try a half. So -1/2 times 3/2 times -1/2 times, okay, half plus 1.4, it's about 1.9, and half minus 1.4, that's going to be -0.9. Okay, so how many negative signs? 1, 2, 3. So this is going to be negative. It's going to have a local minimum here. And I probably need to multiply this out. I just need an approximation. So this is 2. This is about 1. So I can ignore that for my approximation. 1, 2, 3, 8, 3/8. Okay, so here's my 1. I guess that's not so bad. So now I know there's a kind of a minimum here. This seems to be crossing the axis of 0, and if you look at this, it's pretty symmetric too, doesn't it? Right? Except for this, except for the negative x, this piece, whether I put in -1 or -1/2 or +1/2, I get the same value. So the only thing that's going to change is the negative sign. So whatever this is, this will be kind of its symmetric opposite. Again, this seems to be positive over here. We could plug in a value between 1 and 1.4. And we would see this has some kind of local maximum. Again, you know, we could use a calculator, or you could multiply out and find out. At this point, now we can go back and say, all right, we know our end behavior. And the same thing over here. We know our end behavior. All right, we could get, you know, we could be a little more accurate. We could plot some points. We could kind of see how quickly this is moving off. But at least now we have a pretty good feel for what this polynomial is like. All right, let's do one more, a little simpler one. Let's look at f of x equals x cubed is 2x squared minus 3x. It's similar in that it's odd, but its end behavior is going to be different, isn't it? What's going to happen is this function gets very large. It's going to go up, yeah. keep that in mind. And then as it gets very negative, it's odd, it's going to go the opposite direction. Okay. Let's find zeros. This is x times x squared minus 2x minus 3. Which again, because these are made up problems, will factor nicely. 3, 1, minus goes on the 3, and the plus goes on the 1. So its zeros are x equals 0 at x equals 0, negative 1, and 3. So let's plot this. So we have them here, here, and 3. Okay, we know between these points and these points there will be a maximum or a minimum. Again, let's try that point negative a half, just to get a feel for where the max is going to be. So negative a half times 1/2 times half minus 3 is negative 5/2. So there are two negative signs. So I know it's going to be positive. They're going to cancel. And if I multiply that out, I get 5/8. So where's 5/8? That's about here. So that's probably not exactly where the maximum is, but gives us a rough idea. Now we also know that there's going to be a minimum here between these 2 points. So again, let's just kind of guess. Let's try 1/2. So we have 3/2 plus 5, 3/2 times 5/2 times negative 3 minus 1/2, 3/2. Okay, as we expect, there's just one negative sign here. We know this is going to be negative. And we have 9 times 5 is 45, divided by 8. It's about negative 5. That won't even fit on the blackboard, will it? So we've got something happening here. Again, you can always plot more points and get this more accurate, or use your computer or your calculator. You'll see this, but it's not going to tell you how you know this. And of course, we see the end behavior here, as we expect, it's going off positively in this direction and negatively in this direction. All right, that's almost everything we need to know to graph a polynomial. Get a feel for what it's going to look like, what its features are. There's one more trick, or shall I say trickiness about this. It has to do with zeros. And it has to do with the fact that you can have duplicate zeros or duplicate roots. We already have some examples of this we've looked at quite a bit. One of them is f of x equals x squared. We've said a few times, because this is a second-degree polynomial, it has 2 roots. They just happen to be the same value, right? And I can factor this x times x. Either x could be 0 or the other x could be 0, right? So this is an example. Let's take a look at what this function looks like. At the 0 point, the function just kind of lands on 0, but as you go off in one direction, it gets positive, and the other direction it gets positive. In other words, it doesn't cross the axis. This is kind of a prototype example for an even, an even term, even number of duplicate roots. They're going to just touch the axis, but whatever direction they came from, they're going to go off in. It could also be in the negative direction. The other kind of prototype will be x cubed, right? This has 3 duplicate roots, all 0. And what does this look like? Well, it looks similar in the positive direction. But again, it just touches 0, but it does cross the axis. So again, we're going to find that if you have an odd number of duplicate roots, the function will cross the x-axis. Okay, this is something to be aware of. We're going to do an example, an extreme example, and you'll see how this works. To make this example a little easier to deal with, it's pre-factored for us. We're going to look at x to the 4th times x minus 2 cubed times x plus 1 squared. Well, before we proceed, let's think about what the end behavior is. We're going to have x to the 4th, positive coefficient, x cubed, positive coefficient, x squared. So 4 plus 3 plus 2 is 9. It's odd with a positive coefficient. So we expect in this direction, the positive direction will go up, and the negative direction will go down. In between, we see we've got zeros at 0, 2, and negative 1. However, at 0, we have an even number of roots, 4 zeros. At 2, we have an odd number. And at minus 1, again, an even number. So we put in the roots here. So what we would expect is that at 0, it's not going to cross the axis. At 2, it will cross the axis. And at minus 1, it won't cross the axis. That's what we expect. All right, let's pick some number between 0 and minus 1 to see what the behavior is like here. So what would be a good number? Negative a half. So negative a half to the 4th is 1/16. Negative a half minus 2 is negative 5 halves. Negative 5 halves cubed, so that's going to be negative 125 over 8. This is a multiplication, right? And negative a half plus 1 is negative a half is positive half squared, so 1/4. So what do we have here? 16 times 8 is 128, times 4 is 512, negative 125 over 512. Okay, so somewhere in here, this is about a negative quarter. Is that right? That's right. So we have some kind of local minimum. But now at -1, what are we expecting? We're expecting, because it's even, it's not going to cross the axis. So in fact, at this point, it's going to head down, doing our end behavior that we expected. All right, what about at 0? Again, it's even. So we expect that, again, it's going to go down. You might want to pick a point between 0 and 2, about 1. So that's 1. 1 minus 2 is negative 1 cubed times 2 squared. So this is negative 4. So down here somewhere. But now at 2, we have an odd number of roots. So we do expect to keep going, and then it's going to follow our end behavior. Okay, so that's how you have to deal with multiple roots. That's what you would expect to see. When it's even, it's just going to touch the x-axis, but go off back where it came from. And when it's an odd number, it's just going to cross. All right, that's graphing polynomials.